Okay, today's topic is chemical equilibrium. So it's chapter 15, and so I've never done this video online. It's going to be my first time. We'll see how this goes. Chemical equilibrium, chapter 15 is our chapter, and I want to preface this first that there is quite a bit of math in this chapter, and it involves up to quadratics. But besides using the quadratic formula, it's not the hardest chapter in the world. It just does require a bit of math. Okay, so this chapter is on chemical equilibrium. And so a few things about equilibrium. Equilibrium is a state in which there are no observable changes as time goes by. And so what that means is the forward and reverse reaction rates are equal, and it appears that the reactants and products remain the same, remain constant the entire time. So at equilibrium, it looks like nothing's changing, when in reality, something's always changing. What I mean by that is, say for instance, you probably learned a water cycle. Water is evaporating on Earth and it's condensing somewhere else. It's raining or snowing somewhere on Earth and it's evaporating here in LA. Well, last night it rained. But it can't always rain, it can't always evaporate. Well, actually it is always happening. They're happening at equal rates. That means the amount of evaporation that's happening on Earth is equal to the amount of some sort of precipitation that's happening somewhere else on Earth. So because of that, the products and reactants always seem to be the same. What I mean by that is, if you look at the ocean level last week and this week, it looks the same, even though it rained last night. It looked exactly the same. Doesn't mean the ocean's rising because it rained, and somewhere else on Earth it's evaporating. But this is always happening in the chemical equilibrium. The forward and reverse reactions are always occurring, but they're just happening at equal rates. So that is an example that I gave you of a physical equilibrium. When liquid water, H2O liquid, turns into H2O gas, it's happening at equal and opposite reaction rates. In chemical equilibrium, though, it's not just like a liquid turning to solid, but from one chemical, I'll just say, let's call it chemical A, turning to chemical B, and B turns into A, and A turns into B, and B turns into A, and A turns into B. What this reaction is specifically here is the dinitrogen tetroxide here turning into nitrogen dioxide. One of them is a reddish-orange gas. The other one is a clear gas. But it's happening. A turning into B turns as quickly as B turns into A. These forward and reverse reactions are equal, and the concentrations of each one of these are appear to be the same at equilibrium. So that's the definition of equilibrium. But right now I'm going to focus on this reaction. Let's say A turns into 2B, and these 2B turns into 1A. So that's that reaction right here. I'm just going to say A turns into 2Bs, and those 2Bs turns into A. So if I have a container with a concentration where it's just all nitrogen dioxide only, what happens to this nitrogen dioxide? This nitrogen dioxide, it turns into the N2O4, and it starts increasing, while at that same time the NO2 starts decreasing. Well, it doesn't decrease forever, because as this NO2 decreases or the N2O4 increases, now this N2O4 can start turning back into the NO2. And so as this NO2 decreases, this N2O4 increases until it gets to a point of equilibrium in which the forward and reaction rates are equal. Same thing is if I start off with just N2O4. If I start with just N2O4, this thing will decrease while eventually the NO2 will start increasing. Notice the rate at which this increases is more than this decreasing, because for every one N2O4, 2 NO2s are being produced. For every one N2O4 that's decreasing, 2 NO2s are being made. But eventually we'll get to a point of equilibrium where the rates of reactions forward and reverse are equal. Now, what if I had some random amounts of each? One will increase, one will decrease, until I get to the point of equilibrium, where it appears like there's no change. Again, point is, I'm going back to the previous slide, We get to equilibrium when the concentration of reactants and products remain constant. It appears like there is no more change. There is always a change. It's just the forward and reverse reaction rates are happening at equal rates. So therefore, it looks like there's no change happening. Okay, so here's the same three graphs again on that table. And here are their equilibrium concentrations. Now, is there a relationship between this N2O4 and NO2 at equilibrium? If we looked at just these two columns and these numbers, do you see a pattern? And so just think about it if you see a pattern in this column versus that column. Now, if you're like, well, I see that at equilibrium, the equilibrium concentrations, that the N2O4 is greater than that of NO2. Well, yes, you're right. It is always greater according to this table. In case you're like, well, it must be the same ratio. If you did that, actually, no, that doesn't work. But we don't know why. Well, you don't know why yet. But if I so happen to have squared this column, N2O4, then divided by NO2, if I did that, I notice that, hey, it seems like there's no change. It's about 4.6 something times 10 to the minus 3. That is constant. So if I just divide NO2 divided by N2O4, it's not constant here. But if I square this and divide it by that number, then it is constant. So what if I were to square the NO2 concentration, divide by N2O4 concentration, then that is constant. Oh, these brackets here, they're always going to be in molarity. Molarity, again, as defined as moles per liter. So whenever you see a bracket, just realize that's molar concentration, molarity, moles divided by liters. So in the last slide, if I took NO2, squared it, divided by N2O4, it was 4.6 something times 10 to the minus 3. Okay, we've done this with many, many, many different equations, and we always notice that there's some pattern. And the pattern is this. If you have any equation, A and B make C and D, what is constant is this, and this is like one of the big equations in the chapter. What is called the equilibrium constant? The equilibrium constant K, for concentrations, it will be known as Kc. It will be the concentration of C times the concentration of D, all divided by the concentration of A, divided by the concentration of B, all raised to the power of the coefficients. The lowercase a, b, c, d, the lowercase ones, those are the coefficients of the balanced equation. Like in that equation here, the coefficient in front of NO2 is a coefficient 2, and that's why that one is squared. The coefficient in front of N2O4 is a 1, that's why that's the first power. Here, the product C and D raised to the power of the coefficients, lowercase c, lowercase d, divided by a concentration in A and B, all raised to the power of the coefficient A, coefficient B. The main thing is it's the product C and D over the reactants A and B. The product C and D over the reactants A and B. The product C and D over the reactants A and B. The product C and D over the reactants A and B. The product C and D over the reactants A and B. The product C and D over the reactants A and B. The product C and D over the reactants A and B. The product C and D over the reactants A and B. The product C and D over the reactants A and B. The product C and D over the reactants A and B. The product C and D over the reactants A and B. All raised to the power of whatever those coefficients are. It's also called the law of mass action, but if you just call it the equilibrium constant, fine, that works. So there's a few other things. What does this K value mean? It's going to be a number. There are no units to this value of K. So is it like, hey, K, is it 4.63 times 10 to the minus 3 molars? No, there are no units to this constant. We just say it's 4.63 times 10 to the minus 3. That's it. No units. Actually, it makes life a lot easier. Okay, so it's just going to be a number. If the number is much bigger than 1, and that's what the symbol means. It looks like a greater than. What the symbol means is if K is much bigger than 1, we also see that, hey, if K is a really big number, then that means you have more C's and D's than you have A and B. Remember, it's products over reactants. That means whatever concentration C and D are compared to A and B is probably going to be a greater number. We also say the reaction lies to the right, or the products, which are C and D, are favored. The opposite of that, if K is a very small number, this symbol means that K is a lot less than 1. This is kind of a lot less than 1, well, kind of ish. And so we say this reaction lies to the left, or in other words, there are primarily more A's and B's. Another way we also say this is that the reactants are favored. So the equilibrium constant is a number. And if it's a big number, much bigger than 1, then the products are favored. And if the number K, the value for K, is a lot less than 1, we say it lies to the left, or the reactants are favored. Okay, so in homogeneous equilibrium, this applies to reactions in which the reacting species are all in the same phase. What it means by that, let me adjust the screen a bit. Okay, so what it means by that is that they're all in the same phase, that these are both as gases, or they can be both as aqueous, but that they're in the same state of matter. In this case, both as gases. So there's two ways of writing this K. We say it's products over the reactants, but we could do it in terms of concentrations. We call that Kc, and concentrations measured in molarity. Another way to do it is as in pressure. Pressure only applies for gases. So if these were not gases, you could not do Kp if it's not a gas. Kp, the pressure of NO2 squared, over the pressure of N2O4. So the pressure of gases. So you do Kc as concentration in molarity, or you do it as Kp, which is the pressure of each gases. And these are usually done in atmospheres. In most cases, Kp does not equal Kc. So, but it's like, wait, is there a relationship between Kp and Kc? I wonder. Well, since you asked, yes, there is a relationship. The relationship is this. Kp is equal to Kc times RT to the delta N power. And you're like, okay, I know what R is, I think. I know what T is. T is temperature, of course. Temperature, but just make sure it's in kelvins. N, delta N, it's a moles of gaseous products minus a moles of gaseous reactants. Or in other words, the coefficient C and D minus the coefficients A and B. The coefficient C and D minus the coefficients A and B. It's the coefficient C and D minus the coefficients A and B. That's what delta N is. Back to R. Remember when we did all this gas stuff, what R was? R is the gas constant in the gas chapter. R is at 0.0821. Technically liters atmospheres per mole Kelvin, but when we do Ks, we don't need the units, so it doesn't really matter. Okay, so homogeneous equilibrium. If I'm trying to do Kc, again, it's products over the reactants. It's the products over the reactants. The products, CH3COOH and H3O, over acetic acid, that's acetic acid, and water. The only thing is, the concentration of water is constant. Well, also, we usually don't talk about the concentration of water, because when we're talking about concentration, molarity, we're talking about how much stuff there is per liter of this solution, or in this case, water. How much water do we have in our water, which doesn't kind of make sense. So we don't actually include the water into the equation. So one thing we do with all the aqueous stuff, we don't include water in an equation. In fact, later on, we're not going to include any solids as well. Solids and liquids, later on in the notes, we'll see we will not include them in the equation for Kc. So when we have an equation, products over reactants, do not include water into this. So technically it is included, but water is constant. Kc, this is Kc prime. Kc prime is constant, so it's just a constant times constant. It's just one big constant. So in general, again, reminder, we do not include any units in the equilibrium constants. So if you're thinking about including constants, we do not include constants into the equation. Okay, so sample question. here's the sample question. It says the equilibrium concentrations of reaction between carbon monoxide and molecular chlorine to form COCl2 at 74 degrees Celsius. The concentrations in bracket, that means molarity. The molar concentration of Cl is 0.012 molars. The molar concentration of Cl2 is 0.054 molars. And COCl2 concentration molarity is 0.14 molars. Calculate the equilibrium constant Kc and Kp. Okay, so it's actually two separate questions here. Solve for Kc and then solve for Kp. So, here's the equation. You would be given the equation on the test. Obviously, you're not going to have to write Kc and Kp if you're not given the balanced equation. So we'll start Kc. Again, products over the reactants. Products over the reactants. The products over the reactants. The products over the reactants. Kc, these are concentrations, so that's why these are in brackets. Do I know the concentration of COCl2, the concentration of CO, as well as CO2 at equilibrium? Yeah, they're given. They're all given. So therefore, just plug them in. Plug them in, type in a calculator. I found out Kc in my calculator is 220. So that's Kc. So that's the first part of the question is calculate Kc. The second part of the question is calculate Kp. Well, Kp is equal to Kc times RT to the delta N. I know Kc, it's right here, 220. I also know delta N. Coefficients of the products minus coefficients of the reactants. Coefficients of the products minus coefficients of the reactants. Coefficients of products minus coefficients of reactants. The products coefficients, 1. Summed up is 1. Coefficients of reactants, 1 plus 1 or 2. 1 minus 2 is negative 1. So delta N is negative 1. We know R. R is always 0.0821. The temperature was given. It says, where's the temperature? Right there, 74 degrees Celsius. Or add 273, we get 347 kelvins. So Kp is equal to Kc. Kc is 220. Times R times T, all to the delta N power, which in this case it's 7.7. So Kc is 220, Kp is 7.7. So the relationship between them is this equation. There's not that many equations in this chapter, but this is one of them, as well as the products over the reactants, the products over the reactants. Those are the main equations for the chapter. Okay, yet another sample question. The equilibrium constant Kp for the reaction, 2NO2 makes 2 NOs and O2 gas, is 158 at 1,000 kelvins. What is the equilibrium pressure O2 when the PNO2 is 0.4 and the pressure NO is 0.27 atmospheres? So let's just write what Kp is. It's probably the first thing. Kp is the pressure of the products over the pressure of the reactants. The pressure of the products over the pressure of the reactants. The products over the reactants. The products over the reactants. The pressure NO squared, because coefficient 2, times the pressure O2 divided by the pressure NO2. What's the pressure of each of the gases? It's given to us. So just plug it out. So it's given to us. We are trying to solve for, we're trying to find the pressure of O2. So pressure O2, algebraically, Kp times PNO2 squared over PNO squared. We know the pressure of each one of these. It's 0.4 and 0.27. Plug them in. Kp was given. It was 158. Plug in, solve for the pressure O2, and I get 347 atmospheres. Okay, so this is a lot of plug it into the equation, as you can notice. Okay, so now that was all homogeneous equilibrium, if everything was all the same state of matter. But what if things are different states of matter? Then we get what's called heterogeneous equilibrium. Things are at different states of matter. And if things are at different states of matter, heterogeneous equilibrium, then, for instance, here, solids and gases, they're at different phases. That's why it's heterogeneous, because they're different states of matter. Okay, what we did before, we said, hey, I can still do Kc or Kp. Kc, products over the reactants, the products over the reactants. However, the concentration of solids never change. Because one, we do concentrations aqueous solutions. These aren't even aqueous. Solids, solids. Or we do concentration of gases. But we do not do concentration of solids. So they're always constant. They never change. Because of that, we're going to exclude them completely from the equation. We're going to exclude them completely from the equation. So the solid calcium oxide and the solid calcium carbonate, we don't include in the Kc and or Kp equation. In fact, that's one key point. The concentration of solids and pure liquids are never included, are not included in the expression for equilibrium constant. So we never include solids nor liquids in the equilibrium expression or constant. So if you ever see solids and liquids, what I like to do is I just almost cross them out, like they're not even there. So if you see any solids or pure liquids, if you see an S for solid, if you see an L for liquid, I would just cross them out. So what are the only things that we include? We only include gases, and we only include aqueous things. Okay, I'm going to skip this for now because it's not necessary for right now. Let's look at a sample question. Consider following at equilibrium at 295 kelvins. Notice solid, gas, gas. And it says the partial pressure of each gas is 0.265 atmospheres. Calculate Kp and Kc. Okay, since I'm given pressure, I'm probably going to do Kp first. I'm given a pressure of each gas is 0.265. So let's find Kp. Kp is the products over the reactants. The products over the reactants. The pressure of each of the products over the pressure of the reactants. Notice I have the pressure of NH3, the pressure of H2S. I did not include that pressure because that's a solid. We don't include solids nor liquids. What's the pressure of each of these two gases? It says it's 0.265. So plug it in, I get 0.0702. So I plugged it in, and I found Kp. Now to find Kc. Well, here's the equation. Kp is equal to Kc times RT to the delta N. I'm trying to solve for Kc, so algebraically, Kc is equal to Kp times RT to the minus delta N. Here's Kp. R you know, 0.0821. The temperature I know, 295. Delta N. The coefficients of the products. Actually, I should have mentioned, these are only for gaseous products and gaseous reactants. Delta N is going to be 2 because that's on the reactants. There are no gases on the reactant sides. So this is a gas, 1 plus 1, gas and gas, 1 plus 1 are 2, minus 0, that's not a gas. So N is equal to 2 there. Temperature we know is 295, it was given in the question. As well as Kp was 0.027, 0.0702, sorry. This is R, that is T to the minus delta N. I get 1.20 times 10 to the minus 4. And let's see. I don't think we need to do that. We're not going to be doing that. Okay, so some of this stuff we're not going to be doing because this actually technically relates to a chapter that we skipped. And the reason why we did chapter 15 now, it's because it's easier to do this one online compared to some other chapters. Okay, so I'm going to probably pause for now because the next thing is for probably the next topic.